I don't have my digital pad today, so I'm a bit handicapped. But let's see how yeah. Yeah. So we have been discussing scaling down of uh, MOSFET. As I said, by scaling down, I mean, so this is what we have discussed in the last class, but just let me briefly cover what we have discussed yesterday. Uh, so by scaling down, we mean lowering the dimensions of the MOSFET so that more number of MOSFETs can be accommodated on the same silicon area, and that gives us, as I mentioned to you before, lot of advantages. So we will have like increased speed of operation. Of course the cost going to be lower because you can have like more functionality in the same silicon area, okay, and so on. So it has huge benefit, and following Moore's postulate or vision, the blue chip semiconductor companies started to move in that direction. So as I said, there are different approaches to reduce the dimension and other associated parameters of microelectronics or nanoelectronic devices, so that advantages can be achieved. Okay. And we said like there can be constant field approach where we keep the field constant. So if we reduce as we reduce the dimension of the FET, we have to reduce the dimension of the voltage so that the field remain constant, okay, because the field is equal to V over D. So if we reduce D by alpha times, we have to reduce V by alpha times as well, right? Now and that gives us advantages like power dissipation will reduce, okay, power density of course remain the same, but power dissipation will reduce, and delay wise we will get advantage also. But the thing is, as we said earlier, that if we reduce voltage in the same proportion, it will be difficult for the analog design engineer to design the circuit. Particularly, then they will struggle to keep headrooms, enough headrooms, okay, so that all the MOSFET between rail to rail remain in saturation and all that. Then people tried constant voltage approach, but in the constant voltage approach, you doesn't change the voltage, where you are changing or reducing the dimension, that will increase the electric field by the same amount, right? Because you are not reducing the voltage, but you are reducing the dimension. But if electric field increases, at some point there might be breakdown in the device, so that's not good again. And also in this approach, there will be large power dissipation and also large power density. Power density will increase enormously, okay, so that will give rise to a lot of temperature within the chip and all that. So in reality, what the industry is doing, industry is following generalized scaling, where although they are reducing the dimension, okay, in a particular fashion, so that every 24 months you can have like you can double the number of transistor in the same silicon area, but but the voltage you are not reducing that aggressively, okay. So that way electric field will be in between this 1 and alpha, right? Electric field will be in between that, and although power density, power dissipation, everything is going to increase, but the increment is not that high, right? So this is what we have discussed, and then we mentioned like this scaling effect will give rise to a lot of challenges, okay, and we mentioned that some of the challenges we will go through in detail from Rajavi's book later on, but we did mention a particular challenge where we are reducing the thickness of the gate oxide. Why we need to reduce the thickness of the gate oxide? Because we want to have like better gate control, because you know in MOSFET you apply voltage from the gate, okay, that will basically form the channel, and the number of electrons in the channel depends on how much voltage you are applying at the gate, right? So gate has should have a proper control on the channel, and you apply voltage between drain and source, which will basically drain out electron if it is an n channel device, and source electron through the source side, right? But once you are reducing the dimension, your source and drain will be pretty close, so you have to reduce the dimension of the or thickness of the gate oxide, right? Then only your control will remain from the gate side, otherwise you will lose control from the gate side. So if we say mathematically, we need to reduce Tox to keep your capacitance more or less in a healthy value, so that you can maintain this control, right? But if you keep on reducing this Tox, okay, to maintain that control, at some point you will have a situation where we will have like only few atomic layer of oxide, okay? So that can be very detrimental, because that will reduce the reliability of the device. So what we can do, we can uh, replace SiO2 with some high K material. High K means high K value material. So you see in the formula, if we increase K, that will also give higher capacitance, and you can get the control without reducing the thickness of the oxide, right? No, so what people started doing, people started replacing SiO2 with some high K dielectric material. Now, I don't know you know it or not, but or you have heard this or not, the popularity of silicon or silicon based micro or nano electronic device is not because of silicon itself. I mean, of course silicon has a huge role to play, but one of the major component in that popularity is SiO2. Okay, silicon dioxide is an excellent insulating material. Okay, it has very good interface with silicon, maintains very good interface with silicon. Okay, it is not very difficult to make or fabricate silicon dioxide. So silicon dioxide is a very important material over the years. Okay, and that has gives silicon an extra edge over that of gallium or germanium, gallium arsenide or germanium. They don't have stable oxide, you see. So if you want to make the MOSFET with germanium or gallium arsenide, you usually make MESFET rather than MOSFET, metal. Okay, so you can't make MOSFET because they don't have proper oxide. So you see, SiO2 is a very important material, and over the years industries, both universities, research labs and industry has pioneered this technology. Okay, so now SiO2 Si interface is very good, because that interface has to be defect free, otherwise channel electrons or channel holes will suffer, their movement will be affected when they move between source and drain, right? Now you are replacing SiO2 with a high K material, so that is a huge challenge. So that high K material has to have a good interface quality with silicon. That high K material should be able to sustain high temperature, because you see in the microelectronics processes there are several high temperature steps. Okay, so this SiO2, there is no problem with high temperature, but with this new high K material you have to achieve those similar conditions, similar in similar harsh condition it should survive. Okay, now it turned out that HFA2 O2 and ZrO2 becomes two very important material apart from SiO2, which people started using, and industry reported that they got enormous benefit by reducing leakage current, because then you don't have to, if you use such a high K material, you don't have to reduce the thickness of the oxide that aggressively as you do it for SiO2. right? Because SiO2 has dielectric constant around 3.8, whereas here you see HFO2 has a dielectric constant around 6.4, whereas ZrO2 has around 10. Okay, so you see there is clear sorry, I am making a mistake. HFO2 has dielectric constant around 30 to 40, whereas ZrO2 has dielectric constant around 25. So you see clearly around 8 to 10 times these dielectric constant more than that of SiO2. Okay, so that way you make huge improvement in the MOSFET performance, although you are reducing the dimension of the thickness of the oxide, right? Then we moved and discuss a bit of why did we need polysilicon as a gate material above oxide instead of aluminium. That we discussed, because polysilicon can sustain high temperature, so we can use if we use polysilicon as a gate material above the gate oxide, we can make gate fast, and then we can make source and drain, and in that way the gate itself acts as a masking layer. You don't have to make a separate mask and do lithography, because if you use lithography to realize source and drain, in that case, and you use a mask, in that case you have to depend on the resolution of the lithography. But if we use the gate itself as a masking layer, then if you do diffusion or ion implantation to realize source and drain, they will penetrate inside the under the oxide, and the overlap will be maintained between the oxide and the source and drain. Okay, so I mean the gate oxide and source, and gate oxide with drain. So this is what we have discussed in the last class. Now what I want to point out, like initially we started with aluminium gate, okay, then we moved to polysilicon gate. Nowadays we again have moved from polysilicon to metal, okay, metal gate. Okay, in very very these low node devices, maybe 45 nanometer or less, we don't use the polysilicon. Okay, we use metal gate. Now why we are doing that? Because with polysilicon our technology is very mature. Why do we need to replace polysilicon? The reason we need to replace polysilicon is are these two. Okay, I mean polysilicon has a good adhesion and good it is very good material when we deposit on top of gate oxide. Okay, but it is not always compatible when we talk about high K dielectric material, because it's a different material. You see, it's no longer silicon dioxide. So polysilicon is not always compatible with this different high K dielectric material, right? And polysilicon, after all, this is polysilicon, although we dope it heavily to reduce the resistance of the polysilicon layer itself, but the thing is polysilicon is not a metal. It's, after all, it's a semiconductor. Okay, so what happens if right, if you just let me see if I can draw it. I don't have digital pad today. Let me see if I can draw it. So my drawing will be even worse today, but so this is my gate oxide. Okay, now and this is my polysilicon, and I am applying a voltage Vg or Vgs here. Now when it is a short channel device, the gate oxide thickness is very tiny. You see, whether you use SiO2 or use high K dielectric material, the gate oxide thickness is lower compared to long channel MOSFETs, right? Now, if gate oxide thickness is lower, what happens is, if you look polysilicon carefully, it is a semiconductor, and you are applying voltage here. So what happens in this junction here, there will be a depletion region. Okay, on the polysilicon side there will be a depletion region, because this is a semiconductor and you are applying bias. So if there is a depletion region, you see that overall insulating layer thickness is going to increase. Okay, so it will be more than Tox, because this additional thickness of depletion layer is going to add, which will also act as a sort of insulating layer. Okay, along with this Tox, right? Now this is not a problem when it is a long channel device. The thickness of the oxide is quite high, and this thickness of this depletion region is very tiny. Okay, so we don't bother about that depletion region in the polysilicon. But when we have like short channel device, we have gate oxide thickness is very tiny, and that very tiny depletion region in the polysilicon also matters. Okay, so we are reducing the thickness of the oxide to get better control from the gate side, but this additional depletion region in the polysilicon will add to the Tox. So it is basically hampering our goal. Our goal is to control from gate side, and that is why we are using high K dielectric material. We are reducing the thickness of the oxide. Now in every node we are doing that, right? In every next node we are reducing the dimension thickness of the oxide. Now this, as we are reducing the thickness of the oxide, this depletion region at the oxide polysilicon interface adds to the effective dielectric layer. Okay, thickness of the effective dielectric layer. So that was reducing the control from the gate side. So people started replacing the polysilicon again. Okay, so good point of polysilicon is can sustain high temperature. You can dope polysilicon to change the threshold voltage and so on of the MOSFET. Okay, so you can get gate, and also you can get self-aligned gate type of MOSFET where you realize the gate fast. But in the short channel MOSFET, this depletion region reduces the capacitance, less control over the channel, okay, from the gate side. And also it is not compatible with high K dielectric material. You see, it is no longer SiO2. So people started replacing polysilicon. So what we are going to do, we then come back to metal gate again. So we have a oxide, whether it is SiO2 or high K dielectric material, and a metal gate on top rather than polysilicon gate. Okay, now, but you can't use aluminum. You have to use a metal which can sustain high temperature. You see, otherwise you have to go back to that gate last approach, and in gate last approach it is difficult to reduce the dimension of the MOSFET, right? We discussed in the last class. So if we have to use a metal, and we have to make sure that we are doing gate fast approach, right? People tried a lot of different things nowadays. People use maybe 2 or more metal layer. Okay, high K dielectric material, maybe 2 metal layers. Okay, or maybe high K dielectric material, 2 different kinds, 1 metal layer, and so on and so forth, to make things more compatible and so on. Okay, but the thing is, we are moving from polysilicon to metal in the short channel MOSFET, right? Now what we will do, well, we will have gate fast or gate last approach. What is HKMG? HKMG is high K metal gate. Okay, high K metal gate. That is the technology we are using. But we can have like gate fast approach or gate last approach. If it is a gate last approach, we don't have to bother about temperature budget and all that, you see, because then we can use any metal we want, right? As long as the addition and all everything is okay, we can use any metal if it is a gate last approach. But gate fast approach is need of the hour, because if you use gate fast approach, you can keep on reducing the, you'll be able to reduce the dimension of the MOSFET that we discussed in the last class, right? So we saw different industry follow different approaches. For example, Simatech, IBM, okay, these companies, they follow gate fast approach because that is the conventional approach, right? This is a relatively similar to the process flow of the existing silicon dioxide and nitride dielectric layer, right, and polysilicon gate, right? So these polysilicon gate and silicon dioxide gate oxide, as we follow this gate fast approach. So IBM and Simatech and many other industry giants, they started following the gate fast approach. They use high K hafnium based dielectric layer, with dielectric constant, remember, around 30 or 40, right? And metal electrode or metal gate on top of that oxide layer, okay? But you have to make sure that that metal can sustain high temperature, okay? So what is the advantage? Advantage is density is an advantage, because if you have like gate fast approach, you will be able to accommodate more device. You can follow Moore's law, okay, in the future node. And it's a simpler technology, cheaper technology, and so on. So that is gate fast approach advantage. What is the disadvantage? Disadvantage is of course thermal budget. As I mentioned, you have to choose a metal which not only adds has good addition with the dielectric, high K dielectric layer, but also it should sustain high temperature, high annealing temperature, right? The temperature during diffusion and all that. So it should maintain or it should remain intact in all those harsh environment. What Intel did, Intel follow gate last approach, okay? Now, but they follow gate last approach, but they did a clever thing. What is that? They use polysilicon at gate material. So say they form, although it is gate last, but what they did, they form gate oxide, whether it is I think high K dielectric oxide, high K dielectric material. Then on top of that they deposit polysilicon. Now if you deposit polysilicon, you remember you have a thin depletion layer in the polysilicon oxide interface. But what they did, they didn't use polysilicon as a gate contact. What they did, they use polysilicon gate as a masking layer and create the source and drain, okay, annihilate everything, all these processes they have done. Then they remove polysilicon, okay. So polysilicon they have used as a sacrificial gate layer, okay. So they created they deposit high K dielectric material, they deposit polysilicon, they created source and drain. So that way it is like gate fast approach, right? But then what they did, they remove polysilicon. So polysilicon is a sacrificial layer they use, okay. Now they have deposited metal. So that metal, so that way it is like gate last approach, because metal you are depositing at the end. But that metal doesn't has to be like that metal might have like a lower thermal budget. That's not a problem, right? Now this has consequences. What is the consequence? Consequence is advantage wise less thermal constraint, because that metal you are depositing at the very end, right? So you can have choices of different metals. You don't have to choose a metal which only can sustain high temperature. You can choose many different metals, okay. What about the disadvantage? Disadvantage, it is a complex process, because you are depositing polysilicon, you are using polysilicon, and then at the end you are removing polysilicon. So this sacrificial layer polysilicon, this is a little extra step, okay. But you can get like advantage that way, like you can use any metal you want. So industry is divided whether to use gate fast and gate last approach, and people used different approaches depending on their expertise and their innovations, right? Now, I'm just ignoring this slide. We will discuss it later on. Okay. Uh, so one thing is gate oxide. Regarding gate oxide, we discussed that high K dielectric, and we have also discussed gate fast and gate last approach. There are other things also, which is known as we reducing the dimension of the device. If you understand how the carriers are flowing between source and drain, the carriers doesn't flow in a straight line. Okay, what the because there is an electric field. There are two electric fields. One electric field between gate and substrate, and there is another electric field between source and drain. Okay, so the carriers will basically move like this. Roughly, they move like this. They are not moving in a straight line. Okay, now if they move like this, they will basically in other words, I mean, there are couple of things. One is like this is a very tiny channel. Okay, and there is, if it is a p-type substrate, so there is immobile ions here. Okay, immobile ions. So the carriers, I mean the electrons, when they move from source to drain, they will basically interact with these immobile ions. These immobile ions are sitting just underneath the channel. So these electrons, or in case of n-type substrate, there will be holes. That is a p-channel MOSFET, and they will basically interact with these immobile ions. So if they interact with these immobile ions, that basically decrease the mobility. So again, we will discuss this mobility degradation and all that later on from Rajavi's book. But I am tempted to discuss the solution of it now, as we have this slide. So these carriers, when they move between source and drain, they interact with these immobile ions. Okay, and these immobile ions, when they interact, their mobility degrades. Okay, so how to improve this mobility? Now the way people improve the mobility, okay, one of the technique is they use strained silicon. They use strained silicon. So strained silicon, how it works? No, there is instead of silicon, they started using silicon germanium. Okay, germanium has lattice constant little bit higher than that of silicon. Germanium has little lattice constant little bit higher than that of silicon. So if germanium you use, and then on top of germanium, if you deposit or epitaxially grow your silicon, those silicon atoms, they will basically align themselves with already deposited germanium. Okay, you see in this picture. So they have already they are aligned themselves with already deposited germanium. And then what happens? You see the lattice constant of this newly formed silicon, which is known as a strained silicon, will increase little bit, very tiny. Okay, now if it increases little bit, even it is very little, people have shown that that increases the velocity of the electrons, because the distance between immobile ions may be earlier like this. Okay, but when you use short channel MOSFET with a strained silicon, maybe the distance between the immobile ion increases. So that will allow the electrons to move faster between those two immobile ions. So they interact less, or they accelerate more before they encounter another scattering with the immobile ions. I hope you understand that. So this is I mean, this is a very simplistic view I am telling you. It's more complicated, and I don't want to go in that direction like there are different orientation of the crystal, and this simplistic view is not entirely correct, but and it behaves differently for N channel MOSFET and P channel MOSFET. So I just don't want to go into that direction, but if you are interested, you can again look at the net and see how the strained silicon is behaving, and sometimes we create this strain in the source and drain, not in the substrate, and so on and so forth. So let's not go into that direction, but this is a simplistic view, okay, and it helps in increasing the mobility of the transistor. In fact, you see 70% faster the industry reported by changing from conventional silicon to the strained silicon. So that's like a huge improvement. Okay. So what next? I think I just move on. Move on these. So by not only by silicon germanium, people started using other materials also, like indium gallium arsenide has much higher mobility, but that will not give you MOSFET. People started developing high electron mobility transistor, HEMT. It is called HEMT. We will discuss HEMT in detail much later on. But let's move on. It's I will discuss these things if required later. People started making multiple gate MOSFET. Okay. People started making FinFET so that you can get better control from the gate side and all that. Again, we will discuss these things in much detail later on. Okay. So I'm just keeping this slide. This is a slide just to show you that the mobility of the different materials. You see, mobility of graphene is huge. Okay, mobility of graphene is huge, where this is around 1300 in case of silicon electron mobility, but it's more than 1 lakh. Okay, or 0.1 million in case of graphene, say. In Indian gallium arsenide is more than 8,000. So these are different materials. People started venturing those material also to improve the speed of the device. Okay. Right. So not sure, should I discuss these? Right. No, again, let me touch upon very briefly. So apart from silicon, there are other wafers also. One of the wafer is silicon on insulator. Okay. So what is silicon on insulator wafer? On silicon on insulator also you can make your device and circuit and all that. What is silicon on insulator? Silicon on insulator is basically there is a silicon substrate. On top of silicon substrate there is an oxide layer, and on top of oxide layer, which is known as buried oxide, there is another silicon layer which is very tiny. This is known as active silicon. Okay, this is known as active silicon. So this active silicon basically contains all the devices, whereas this silicon which is underneath the buried oxide, okay, this is known as handle silicon. Okay, handle silicon. So this handle silicon basically gives the stability or mechanical stability, because this is much thicker, maybe few hundred micrometer thick. Okay, whereas this tiny silicon is very thin, maybe few micrometer, even few hundred nanometer, few tens of nanometer. Okay, so this kind of wafer, and rest of the thing is same, like gate oxide, polysilicon, different metal layers. You see different metal layers is there, then the insulating oxide layer. Okay, so this is top oxide, the top silicon nitride. All these layers are same, which is present in the CMOS conventional wafer, silicon wafer. But in silicon on insulator wafer, the reason I'm discussing this, I'm coming in a minute, but this is one of the, again, one of the breakthrough people made in microelectronics or VLSI fabrication. So two breakthrough we have already discussed. One is like high K dielectric, The second is like strained silicon, and third you can say silicon on insulator. There are innumerable breakthroughs, and we will not have time and opportunity to discuss all, but I thought that I will discuss some of them which are very major breakthroughs. Okay, so this silicon on insulator wafer is little bit different compared to conventional CMOS wafer. In conventional CMOS wafer, this buried oxide is not there. You see, this buried oxide is not there. So instead of buried oxide, what we have is like a complete silicon wafer, no buried oxide. And on at the end of the silicon wafer, you will have like let me, can I back discard. So don't know. Yeah, so you see here, this is a conventional silicon wafer. So I have a p-type or n-type substrate, and in that you make a make your MOSFET. But in this case, what you have, what we in silicon on insulator, you have a silicon which is used only for, because this silicon is very thick, few hundred micrometer thick or silicon. Okay, and the device you are making only in fast few, maybe few micrometer, a few hundreds of nanometer, within that you are making the device, right? But when you, so for device perspective, you don't need this much thick silicon substrate, but you need silicon substrate to make things stable. If you, because if you see by 12-inch wafer, for 12-inch wafer, if you have like a silicon wafer thickness of 1-2 micrometer, the wafer will break, right? So as you have like, instead of 3-inch, 4-inch, if you have like 12-inch wafer, the thickness of the wafer has to increase to give mechanical stability, right? But for active, for the device making, you use just very thin top layer, right? Top silicon layer. So that concept you use here, what is that? Yeah. That concept you use here, you keep the thick silicon wafer, which is known as handle wafer or handle silicon. On top of that, you grow buried oxide, that is thicker oxide, 1-2 micrometer thick, depending on your requirement. And then you have a thin silicon layer, which is known as active silicon. You use that silicon to make your device. And in fact, you can remove silicon in some places. You see here, there is oxide layer, ILD, insulating dielectric layer, basically ILD. Okay, so that's basically oxide layer. Okay, there are other dielectric layers also people use between different devices. So here you see, if you etch out silicon in between the devices where you don't need silicon, you will be able to reduce the crosstalk, you see, between devices, because there is no silicon. Whereas that you can't do if you have a conventional CMOS or silicon wafer, because you can't etch out silicon between devices, because all through that is silicon. But here there is a oxide layer and a very tiny silicon layer which you can etch where you don't need your device. So there, this is a device, this is a device, this is a device. So you remove other part where you don't need silicon, right? So that is one advantage. You will be able to reduce the crosstalk. Okay. There are other advantages of SY wafer. The reason I am discussing this, because this has huge implication to reduce the device dimension. Okay, why it has implications? Because you see, in the conventional MOSFET, you have like other capacitance also. Where are they? How to draw? Okay, so you see, all these capacitances. One of your friend asked yesterday, like these, all these capacitances are not good, they are detrimental. Okay, so you see, this is my conventional MOSFET. Okay, and there is a depletion region here. So this is my source, underneath the channel there is a, underneath the drain. So this depletion region, so you see, there is a capacitors between my source and substrate and drain and substrate. Okay, and this is a depletion region. This is N plus, this is P. So these form a capacitance. So we don't want this type of capacitances. Okay, all these parasitic capacitances, they will ultimately create problem if you have like high frequency circuits. Okay, so if you want to use your devices in high frequency region, this will create problem. So when you are reducing the dimension or making the short channel MOSFET, one of the advantage you want to achieve is high frequency, right? Although yesterday we say we don't aggressively increase the oxide, increase the clock frequency, but we like to increase it, right? I mean, we don't increase that aggressively, but if we want, if we can, we will increase it, right? So the reason we don't increase because that aggressively, because that will increase the temperature of your chip. Now, if we can reduce uh, these capacitances, source with substrate, drain with substrate, that will improve your device performance. So how you can do that? If you look carefully, your this uh, this SY based MOSFET. SY based MOSFET looks like this. Okay, so this is my N plus source, N plus drain. Okay, and depending on the thickness of your active silicon layer, the buried oxide may be very close. It's maybe here. Okay, so this is my buried oxide. So this is my buried oxide. Then there is handle silicon. So you see now the the capacitance here. Okay, capacitance is very, you manage to reduce is drastically, because you see this, the depletion region is almost here, depletion region. Okay, and your entire active silicon layer is depleted almost. Okay, there is a channel here, your entire active silicon layer is depleted, active silicon layer, and then there is this buried oxide. So the thickness of this dielectric, okay, which is depletion region plus this buried oxide, will reduce this capacitance drastically. Okay, so you see, you manage to scale down the device without damaging the high frequency application, right? So this is one of the advantage of SY. Another advantage is you manage to reduce the crosstalk between different devices, because these silicon and this silicon no longer connected. So they are no longer like leakage current between one device to another, and so on and so forth. So I have jotted down several advantages, but I'm just keeping it for the time being. So you see, I have mentioned reduced leakage current and crosstalk, reduce parasitic capacitances that I have just now discussed, which will improve the device performance. IBM reported 20 to 35% increase in the chip speed if you use a SY wafer compared to bulk conventional CMOS technology, right? And because of this leakage current, low leakage current, your power consumption will reduce, right? All these advantages will help you to reduce the device dimension, right? So it has been established that the performance of 250 nanometer node of SY is equivalent to 180 nanometer node of CMOS. You see, so without reducing the dimension of the MOSFET, you can achieve like similar performance, right, in SY. But SY wafer is expensive because it is like additional process step you have to do, right? This oxide, so the fabrication is a bit complicated, so that increases the cost, and if you use more and more SY wafer, the cost will decrease, and so on and so forth, right? But nevertheless, the cost of SY wafer is more than that of the conventional CMOS wafer, right? Let's discuss little bit different things. Again, this part you know, although I don't know you know it in this fashion, but we are very smart now, you use very smart electronic gadgets, and this part you known to you. But let's look at a little bit different perspective as far as the Moore's vision is concerned. What Moore said, like we need to double, at least double the number of transistors every 2 years. Okay, every 18 to 24 months we have to double the number of transistors, right? That's very good actually. So all these advantages we can get, and there are a lot of challenges. We have discussed some of the challenges and how we can improve things, that also we have discussed little bit. But the thing is, if I jot down some of the challenges, you see that unsustainable power dissipation, huge power dissipation in a tiny area, temperature will be enormous, okay, of that small tiny chip. You see your nowadays very hi-fi state of the art processors, you need some kind of cooling arrangement, okay, whether you use fan or some other technique, you need that, right? We are moving in a direction where the source and drain is so close, okay, maybe there are just only few atomic layer between source and drain. So it is not easy to fabricate such devices. It's not easy, okay, it's very difficult, it's highly expensive. Every 2 3 years you need to develop a new technology, which is not easy, because when you sell something, it not only the price of that component, the price of that chip depends on many other things. Price of the chip depends on how much research you have carried out, what is the in the back end, okay, how much manpower involved in that research, okay, what are the new equipment you develop. All these come into picture when you ultimately sell that device or sell that circuit or sell that processor, right? So price reduction in price is not easy, it's very very difficult, particularly because you need to innovate things, okay, in an unprecedented scale, right? And as you are going down and down and down in the MOSFET dimension, there will be lots of process and device variability. It's not easy, like because if your gate length is 2 micrometer, few tens of nanometer device change here and there, dimension doesn't matter. But when your device dimension is in the nanometer regime, less like 22 nanometer, 14 nanometer is device length, you understand the kind of resolution and kind of accuracy we are looking for, and they're bound to be device variability, and small tiny device variability will change there will be the change in the MOSFET current and all that, okay. And and as we keep on reducing the size, we will see that no real performance increase we ultimately get. I mean, initially it was okay, for last several 2 3 decades it has been excellent, right? But ultimately now we are not getting enough, we are not getting value for money, okay. We are not, this the amount we spend to develop and innovate new technology so that we can move from 22 to 14 nanometer gate length, or 14 to 7, or 7 to 3 nanometer. It has been unprecedented, the amount of research and innovation and money you need to spend. But in reality, whatever you are getting out of it is not is like value for money, right? So what you do, what we are doing, so industry now moving in a little bit different direction. I'm now is an exaggerated term. Industry has been moving in a direction for last 10 years or so, okay. I don't know, you use Nokia's phone, Nokia's mobile phone. Nokia had mobile phone, I mean still they have it. Yeah, I remember I was using 2003-4. The Nokia has a tiny mobile phone, very tiny, very robust. If it fall from the pocket, um, no problem. It will work. It's very very robust, very tiny, small screen, maybe 2 inch by 2 inch screen. You can phone, you can talk, but you can't do anything else. I mean that time in 2003, 4, 5, 6, it was just perfectly fine. But then people manage to, or there is a requirement from the customer side, like what else we can do from these electronic gadgets. And now you see we have phones, you can do video chat, you can listen to music, I mean you can listen to songs, you can listen news, and all that. Okay, you have it packed with different sensors, and so on and so forth. So nowadays electronic gadgets has many different functionalities which it didn't have 10 15 years ago, right? So you see, now we are not saying more means we are reducing the dimension. We are talking about more than more. What is that? We not only want to reduce the dimension, we want more functionality. Okay, we want more functionality. So even if, but this more functionality will make things little bit bulky. Okay, so that Nokia phone I'm talking about is very tiny. It easily go to your pocket inside. Okay, very small screen just to see which number you are dialing or who is calling, this much. But nowadays your phone is maybe 6-inch 7-inch screen, so that makes things little bit bulky. You are basically accommodating different sensors, different names based devices, RF devices. So those are not conventional, those are not always use conventional electronic circuits. Those use something else as well. Those are not belong to conventional CMOS. So these sensors maybe, or maybe optical devices, those are incompatible with CMOS. Okay, you can't go to CMOS foundry, conventional IC design for IC fabricate foundry like this TSMC, Gover foundry and all that, and ask like I want to make a sensor which is an optical sensor, say for example. They will not able to do that because the conventional silicon process line is not ideal or not suitable for those kind of sensors and those kind of different devices. Okay, so if you add those functionality, that will create some additional challenges, but that is like a way forward. That is like a way forward. So we look for to get more from more than more is a must. We are moving towards a direction where our motto or goal is not only to reduce the dimension of the conventional MOSFET or electronic device. Our goal is also how to accommodate or how to integrate with these ICs, other devices, other sensors, other circuits which are not made using the CMOS, using the conventional microelectronics facility. Okay, so the industry is moving in that direction. We are happy because it gives a lot of avenues to move. Okay. So this is again just a slide just to show that we are in a digital world which goes for different performance functionality. Of course, power matters because we don't want to charge our device every now and then. Okay, and so on and so forth. So I think I will stop here today with this slide that you see. These are process node: 130 nanometer, 90 nanometer, 65 nanometer, 45 nanometer. These are gate lengths, right, for every future node. And this is the direction where if we follow Moore's law, we are progressing. Okay, and there is another direction which is more than Moore, where we are trying to add different devices and systems. Okay, the system word is important. Divided devices and system. So ultimately we move in a direction which is in between. Okay, in between. In one hand we are reducing the device dimension, and in another hand we are adding different functionality. So so in this direction we are heading, or the industry is heading. So I think I will stop here. I think I have talked too much. 12:57 now. If you have any queries, just we can take 1-2 questions. I think then we'll stop it. Okay. Any doubt you have? Any doubt? No doubt? Okay, if you do not